Hello, my name is Lydia Joukowsky, and I'm excited to talk to you about low-tech process-based restoration. I'm currently a graduate student in the Watershed Sciences Department at Utah State University. Here's our roadmap for today. Primarily, I'll talk about the scope of the problem, a shared vision, and then define what a riverscape is. Lastly, I'll break down process-based restoration, then discuss riverscape and restoration principles. This diagram on the left is a schematic from 1934. I hope you keep it in mind. On the right is a postcard depicting gravel harvesting from over a century ago on a beautiful multi-threaded river. To effectively implement LTPBR depends on having a broad conceptual understanding of the scientific concepts upon which it is based. And since riverscape restoration is not new, we can learn from others and consider common pitfalls. So, by using this not so new approach, we will have the ability to tackle big problems. For a self-sustaining ecosystem, the government has even utilized beavers' ability to save water. In the 1950s, state land managers once used a surplus of parachutes from World War II to transplant nuisance beaver. Despite some mishaps, the mission was a general success. Thankfully for beaver, we've developed other methods for relocation. Now, let's dive into the scope of riverscape degradation. The scope of degradation is massive. Tens of thousands of miles of riverscape are no longer able to sustain ecological functions or physical, chemical, and biological processes. 1/3 of all rivers in the U.S. are degraded, and by diminishing the processes, our riverscapes are no longer able to provide ecosystem services that humans and wildlife use. So, I come to you with a shared vision. I hope you're here because you have a shared vision of a resilient landscape to climate change. This modern water cycle was presented last year at the Symposium by a team from BYU. I like to use it to emphasize the two-way connection between humans and water. Riverscapes are the product of regional geology, biology, and climate, and is also referred to as the valley bottom. This graphic on the right is a way to conceptualize that riverscapes are created and maintained by just a few dynamic processes. So to make it clear as mud, the valley bottom is a relatively flat surface that is subject to the reworking and influence of current processes. The importance of wadable streams is often understated and overlooked. Sometimes referred to as low order, but certainly not low in productivity, wadable streams are the origin for larger order rivers like the Colorado. And it is well documented that these low order streams contribute to the biodiversity of river networks, are important carbon storage zones, and are important controls on water quality and quantity. Since wadable streams are the dominant river type, there is a great opportunity to increase restoration by focusing on low order streams. I'm going to define structural elements as discrete objects that directly influence hydraulics from Joe Weed. Another way to say that is structural elements influence the physical, chemical, and biological processes that are vital for a healthy or a functional riverscape. This image shows the dynamic feedback loop created by considering the basic processes of any river. But overall, structural elements like wood accumulation or beaver dams forces a cascade of processes that result in a more biodiverse riverscape ecosystem. This image shows a riverscape that appears to be in good condition due to the abundance of riparian vegetation, but it's characterized by simplified in-channel habitat, low channel floodplain connectivity, and efficient conveyance of sediment and water. The channel over time has been artificially straightened, then has been restricted the amount of free space in the valley bottom, and then allowed to recover from intensive land uses. However, the riparian vegetation is effectively protecting a degraded simplified channel by armoring the banks, and it provides relatively little wood to the channel to obstruct flow and force more diverse habitat. So look at this stream. Do you think it's structurally starved? For a long time, I couldn't figure out why this is considered to be an unhealthy stream. But spoiler alert, it's a typical example of a structurally starved stream. Why is that? Many streams appear to be healthy due to a healthy riparian vegetation, but lack the processes of wood recruitment and accumulation. So what constitutes a healthy riverscape? Can you count how many beaver dams there are in this river? This is what the continent's rivers used to look like before land use changes and before the decline of beaver population due to unsustainable trapping. Pre-European settlement, with over 100 million beaver, North America largely looked like this. This abundance of beaver dams, large woody accumulation, created step pools, meandering side channels, and floodplain habitat that dominated the landscape and impounded thousands of acres of feet of water. The biggest takeaway is that we have an underappreciation for what we used to have. We have an appreciation for the simple channel, but not the multi-threaded channel. This has caused a decline in structural forcing across our riverscapes. After scientists reconsidered what our landscape used to look like, the output was process-based restoration, the conceptual framework which argues for the management of processes, not form, when engaging in habitat restoration. Guided by a stewardship mentality, LTPBR allows the rivers to be adaptively managed over time and in response to environmental feedback. This is vital to achieving our goal of encouraging a self-sustaining dynamic ecosystem. Let's relearn what a healthy river is. A healthy stream is dynamic. They are always shifting position within their valley bottom, reworking and interacting with their floodplain. Structural elements force changes in the flow patterns that produce diverse habitats. Heterogeneous landscapes are more resilient to disturbances than simplified, homogeneous landscapes. The relative importance and quantity of structural elements varies based on valley setting, flow regime, and watershed context. Finding a stream relatively similar to your own is a good start for preparing realistic designs and expectations. Lastly, hydrologic inefficiency is the hallmark of a healthy river system. When water has more diverse residence times in the valley bottom, it produces habitat refugia. We're trying to replace log jams, fallen trees, and beaver dams. It should resemble a naturally messy system. A large number of smaller structures working in concert with one another can achieve far more than a few isolated, overbuilt, and highly secured structures. Many small structures provides redundancy and reduces the importance of any one structure. Vital to this is working with natural materials. And as opposed to diesel power, stream power is the driving force, giving the riverscape and/or beavers the tools to promote efficiency allows for restoration to scale to the scope of degradation. Wherever possible, let the system make critical decisions. And lastly, low-tech restoration in and of itself is not a long-term solution. Rather, the actions are intended to initiate processes and kickstart the system towards the ultimate goal of building a resilient, self-sustaining riverscape. BDA structures have really not changed over time. Look at how similar these schematics are. On your left is a handbook published from 1934 by the USDA. On your right is from the LTPBR Riverscape Restoration Manual. Post-assisted log structures, or PALS, and beaver dam analogs, or BDAs, are both intended to address the broad impairments of structural starvation in wadable streams. But a bonus is that they can be used to mitigate against a range of more specific impairments. PALs and BDAs are permeable temporary structures built using natural materials, and they're best when implemented in high numbers. Also, They can be built with or without posts, which has more recently come to light. BDAs differ from PALs in that BDAs create ponds using a variety of fill materials, while PALs are built with only woody material. In practice, PALs can force the same processes of channel widening and aggradation as BDAs. And overall, PALs mimic and promote the processes of wood accumulation, while BDAs encourage step pools and beaver activity. Natural infrastructure in dryland streams help store water, sediment, and carbon. They help promote the same processes as BDAs and PALs. They also have a variety of names. I'm excited to share that while preparing this presentation, I found that 15 projects had yet to be uploaded to the BDA Explorer website. 100 structures have been installed over the past 5 field seasons. 200 amazing volunteers have worked with over 14 organizations in Utah. The next slideshow by Rachel Nichols will show you a project that's happened in Fishlake National Forest. The overarching goal is to improve the health of as many miles of riverscape as possible to promote and maintain the full range of self-sustaining riverscape processes. I'll remind you here that riverscape principles represent an understanding of what constitutes healthy riverscape, which in turn helps us define what restoration should be aiming for. And restoration principles influence the choices and approaches we as land managers take in planning and designing future restoration actions. In conclusion, the valley bottom is a watershed-spanning ecosystem. To take care of the riverscape, special focus should be on restoring floodplain and side channel habitat. Process-based restoration focuses on restoring physical processes that lead to healthy riverscapes. Hand-built structures using local materials can help increase groundwater flow, create more diverse habitat, and provide relief from natural disturbances. In order to address the scope of degradation, it will require that practitioners let the system do the work. Scientists have found that in tandem with installments, priority should also be taken managing livestock grazing, applying controlled burns, and supplementing riparian and meadow vegetation planting. I highly recommend the manual and the pocket guide for purchase. Resources online are available, which provided me a lot of the information to complete this presentation. Thank you so much for your time, and I am excited to answer your questions after Rachel's presentation.
Hello, I'm Rachel Nichols, the hydrologist on the Fishlake National Forest. I'm going to be briefly talking about an example of a low-tech process-based restoration project that we started on our forest last year. This work took place in North Fork Box Creek on Monroe Mountain. I started my position on the Fishlake last spring, and this project was already being planned by Michael Damon, the previous forest hydrologist. The stream was chosen for a variety of reasons. There was lots of historic beaver dam activity on this stream. In the mid-2000s to 2010s, populations started to decline, likely due to drought, overgrazing, and fire. Because of this, the channel has become incised, disconnected from its floodplain, and we're seeing lots of bank failure. These beaver dams also provided deep water habitat that is really important to the trout and boreal toads. We also had lots of materials to work with on site, like willows. We plan to build a series of structures along a mile stretch of the stream. Based on what we wanted to accomplish at each spot, we did a mixture of bank-attached, channel spanning, and postless beaver dam analogs and post-assisted log structures. We installed 16 structures over 3 days. This summer we plan to measure stream flow upstream and downstream of the structures to see their water holding capacity and any impacts to downstream water users for these types of projects. We also plan to add more structures upstream because we have more posts on site and a valid permit. The top photo is a channel spanning BDA. The goal was to slow water through the incised stream section, reconnect it to the floodplain, and catch sediment. The bottom photo was a bank-attached, post-assisted log structure. This was to act as a bank blaster to erode it down and accelerate lateral widening. These are the before and after photos for the first structure we made. This portion of the stream was incised, so we again wanted to slow down the water, have it back up onto its floodplain, and get more riparian plant growth. When I visited the site 3 months later in November, we can see water is slowed moving through the structure, with more ice forming on the upstream side. For some sites, like the photo on the left, we weaved through willow, pine, and sod where we wanted water to pool and slow and collect sediment. Other areas, like the photo on the right, we just used large woody debris where we wanted to add some complexity back into the stream or divert flow. This structure was to act as a bank blaster and accelerate lateral widening. In some spots, we attempted to tie into old beaver dams. These spots were either abandoned or were blown out, but hopefully with a post and a series of structures they can hold in place better. I wanted to thank everyone that helped out with this project. This was a collaborative effort between Forest Service employees, multiple NGOs, and YCC students. If you have any questions about this project or would be interested in helping us build more structures this summer, please reach out to me. Thanks.